Okay, so last week we did some more cardinal arithmetic and saw that this plenty of depends, saw that the axiom of choice was useful for being able to do cardinal arithmetic in particular because it enabled us to use Aleph numbers as notation of arbitrary infinite cardinals. So that was an application of the axiom of choice, or a collection of axioms of the axiom of choice to set theory. But of course, the axiom of choice is not there because it's useful for set theory. It's there because it's useful for mathematics. So I thought we would have one lecture in the course, which is today, about applications and consequences of the axiom of choice for mathematics. Now, the title of the lecture is Mathematical Consequences of the Axiom of Choice. And we're going to begin with just a list of results that you may be aware of already, or some of which I'm going to tell you, of theorems that require the axiom of choice to prove, important theorems that are viewed as important theorems in mathematics. So, I mean, maybe we could just have suggestions from you. So, are you aware of such theorems in mathematics? Require the axiom of choice and sorts of theorems one uses in the background of other mathematics.
The Zorn's lemma count is given.
Well, we'll count Zorn's lemma as part of set, but it is useful in mathematics. In fact, most of the theorems I'm going to talk about, one would prove them using Zorn's lemma. So Zorn's lemma, we've already done Zorn's lemma 2 weeks ago. I view that theoretic tool for proving consequences of the axiom of choice. So I mean, sort of theorems that really say things about mathematical subjects. Yeah,
I think I have 2 or 3.
Okay, very good. No.
The Banach-Tarski paradox, or like the theorem.
Okay, and the Banach-Tarski theorem.
Yeah,
that's going to be a very big topic today, so we'll save that. I won't put that on the board now because we're going to cover that in detail.
Okay, that every vector space has a basis.
Okay, that's a good one. So this is from linear algebra. Every vector space has a basis. And, so once you have a basis, you have a canonical way of writing vectors as linear combinations of basis elements. Another way of looking at it is when you have a basis, a vector space is free-module over the field that underlies the vector space. Over the set that is a set of base vectors for the basis. So another way of saying it is that every vector space is every module, because the modules are the vector spaces, every module is free over a field. It's a more algebraic way of saying it. So one can prove this using Zorn's lemma. You basically consider subsets of the vector space consisting of linearly independent vectors and non-zero vectors, and you put just the inclusion partial order on those, and you show that it satisfies that partial order satisfies the premises of Zorn's lemma. So Zorn's lemma says we have a maximal element, and such a maximal element can prove to be a basis for vector space. Furthermore, this theorem is actually equivalent to the axiom of choice. So not only is it a consequence of the axiom of choice, but from this seemingly innocuous truth, if you like, about vector spaces, we get back the axiom of choice. Okay, you said you've got another one?
Yeah, I think it's, you mentioned it a couple of times, finite ideal theorem, something like that.
Aha, right. I don't know if this is exactly the same. So I've got two ideal theorems in my list. So let's put them. So one is Kroll's theorem in ring theory. And this says every non-zero ring has a maximum ideal. And once again, you prove this by Zorn's lemma. Unsurprisingly, you take a set of ideals. You show, again, you order that by inclusion. You show that that partial order, again, satisfies the premises of Zorn's lemma. Therefore, there is a maximal ideal. Well, and that's what we want to prove. There's nothing more to show, because what we want to show is that there's a maximal ideal. This is not equivalent to the axiom of choice. This is weaker, I think. But anyway, it's been tried by the end. Okay, any more from you? So there's a very famous one in general topology, theorem about compactness. So what's the theorem called Tikhonov's theorem? Does anyone know what Tikhonov's theorem says? You're not topologists. Right. So it says any Cartesian product, including infinite ones, which are the interesting ones in this case, with the axiom of choice, any Cartesian product with a product topology of compact spaces is again a compact space. So compact topological spaces are preserved under product. Compact topological spaces, topological spaces. Those don't. Cartesian products. And again, this one is actually equivalent to the axiom of choice. But actually, it's equivalent only in equivalent to the axiom of choice if you really mean this, but arbitrary compact topological spaces that are compact. Topologists normally like to work with Hausdorff spaces, and this statement for Hausdorff spaces is weaker. Yeah, it still needs the axiom of choice, but is weaker than the axiom of choice. So the Tikhonov theorem is not usually used in the full generality that requires the full axiom of choice. There are also some very famous theorems in functional analysis. For any of you do functional analysis? Okay, so one called really important one, the Hahn-Banach theorem. Again, this is not equivalent to the axiom of choice. That's another related result that's also important in functional analysis called the Banach-Tarski theorem. Also requires the axiom of choice, and that theorem is equivalent to the axiom of choice. Anyway, let's not go into functional analysis, but just to say this is like a really central result in functional analysis. We've also heard Banach's name twice now. Banach and Banach-Tarski. Our different lectures have had different heroes. We started, Cantor was our hero initially in the course. Banach is going to be the hero of today's, a main protagonist in today's lecture. is going to appear many times. Okay, the other one I've got here is another ideal theorem. So here there's a maximum ideal in ring theory, which is standard maximum ideal theorem that algebraists are familiar with. There's another important one which is to do with Boolean algebras, and this is called the Boolean prime ideal theorem. One question how you write Boolean, because it's derived from the name of George Boole, who wrote the famous treatise on the laws of thought, where he basically introduced propositional logic, particularly propositional logic in introduced on law of thought. So one should really write with a capital B because it's derived from the name. One normally does. But there's a train of thought that once the word gets sufficiently established that it's derived from the name, but it's almost like a higher honor now not to put the capital letter there because it's just such an established concept. And, one can talk about Boolean logic in everyday conversation. People know the degree of what you're talking about. Anyway, the Boolean prime ideal theorem, we'll meet this later in the course. So it's another existence of a sort of ideal thing. So this is again a consequence of the axiom of choice. It's not equivalent to the axiom of choice, but this is a very important statement because this statement is, for example, equivalent to to Tikhonov's theorem for compact Pascal spaces. So the version that's typically used by topologists. I think it's equivalent to Kroll's theorem, but I'm not sure about that. This theorem is also equivalent to the compactness theorem for first order logic with respect to arbitrary models. With respect to arbitrary, they're not countable signatures, but arbitrary signatures. And this is just the tip of the iceberg. So one has lots of consequences of the axiom of choice in mathematics, and basically mathematicians use such things without thinking twice. And it's not like something like every vector space has a basis. It's probably hardly ever really used because when you're working with a vector space, you typically do have bases available for it. The Hahn-Banach theorem, however, is used all the time by functional analysts. Anyway, one sees these are major results, and the axiom of choice is, because of this, very firmly embedded within mathematics. Yes,
All of this at least require the axiom of choice to be proved, or can they be proved in a more difficult way? Yeah, without.
Well, as I say, these two are equivalent to the axiom of choice.
Yeah.
You can prove that none of them. So there are models of set theory that do not satisfy the axiom of choice in which all results fail. I don't know if they all fail simultaneously, but for each of the results, you can find a model of set theory without choice. So they all require something. But some of them are equivalent to choice, and for the others, the Boolean prime ideal theorem is weaker than the axiom of choice, but that's equivalent to many statements too. So that's a weaker principle. Sorry, it's not equivalent to the axiom of choice, but it is equivalent to many of the other statements. Right. And one can view somehow the consequence of this is that it would kind of be possible to do mathematics without choice. You would just have to, when you use a vector space, you would have to say, and here with instead of for an arbitrary vector space, you might need to say for an arbitrary vector space with a basis, even for for Tikhonov's theorem, you can say for spaces that for which we can prove the product is compact, and one can make workarounds, but obviously that would make mathematics clumsier. So that somehow, in these cases, the axiom of choice serves to make mathematics, make math highly helpful. It has good consequences, but make maths into a very coherent body. So what I want to spend more time on today is the other side of the coin, which is what I view as the discomforting consequences of the axiom of choice. So things that make you, here you get a nice result that you'd like to have. But now we're going to talk about results that at least make you sort of take a deep breath and think about them. And we're going to look at two such results, and they're related to each other. They're both to do with concept of measure. So not like there are many of you in the room, but how many of you have met the abstract concept of measure, either in a course on measure theory or in a course on probability theory? Good? Just two of you. Well, we don't need to know what it is. The lecture is going to be self-contained. Point is that one can't do some things that one would intuitively like to be able to do. So the first result we're going to meet is the result called Vitali's theorem. And we can view that as addressing a question. And the question is, is there a well-behaved function from arbitrary subsets of the real line to the set of non-negative reals together with infinity, we're throwing an infinity in here, that measures the size of the subset given as an argument. We can view size as length, if you like, the amount of length taken up by the subset, because the real line is like this, stretching up to infinity. And suppose our subset kind of looked like this. There's a sort of way in which you can imagine we can measure the length of the blue bits. So we're ignoring all the red bits, but measure the length of the blue bits and give that, in this case, it would be a finite number because it's only taking a finite amount of space. And in fact, this subset here, so the blue subset, in this case, the one I've drawn, is actually the subset that goes from 0 to a quarter. This is a quarter. And then, so basically, it takes a quarter of the real line, and it misses out the next quarter, and then it takes a quarter of what's left. Hang on, a quarter of what's left. So a quarter of what's left is going from a half to 5/8. Then it misses out the next interval of the same size, and then it carries on from 3/4 to a quarter of what's left, which is now 4, 2. I look at my notes. I hope this is the same set I've got in my notes. 5/8, yeah. 13/16 apparently. That's correct. And we carry on like this. And these are all disjoint subsets, as you can see. And in this lecture, and I've already been doing it in the course, but I'm going to make very heavy use of this notation. In this lecture, I'm going to put pluses in unions in the case that we're unioning disjoint subsets. Okay, so this means a disjoint union. So the result of the operation is exactly the same as the union. The role of the plus is just to emphasize that that these unions are. And we would expect for this blue set that we expect to have the size lambda of the blue set. Oops, is what? What would we think of the length of this set? So we want to add up all the bits of length.
Okay.
Aha, yeah, because this has length a quarter, this has length an eighth, this has length 16, this has length of 1/32. So it's yeah, 1/4, 1/2. Well, quarter is made because each time the next summand is half the previous one, and you know, very easy that adds up to a half. Okay, so such a set we can easily assign a value to, but the question is there a coherent way of assigning a value to every subset? Obviously, some subsets are going to get infinity, like the whole real line itself will get. So we're going to give some criteria that we would like our length function to satisfy. So let's actually just state the theorem. So I'm going to write Vitali's theorem again. And this is actually the theorem. The previous time I wrote it, it was just introducing that that's the topic that we're going to talk about. So the theorem is going to be that you can't do this if you make some reasonable assumptions. So there is no function from mapping arbitrary sets of reals to putative length satisfying some reasonable conditions. So the first one is if we apply lambda to the open interval AB, I mean, if you want, put another bracket around that, but if somehow don't like to double brackets, so lambda applied to the open interval AB is going to be so where, in order to have such a thing, we'll assume that A is less than B. So it's going to be what? If B minus A. And now we're going to, nobody objected to this. And the idea is whenever we have a countable collection of disjoint sets, then we should be able to sum their length. Notice that there's a canonical notion of countable sum on 0 infinity. You can add for any countable collection of elements from 0 infinity, count the infinite elements, you can always add them and get a value from 0 infinity back. You know, quite often you get infinity. If you get, if you're in a nice situation like you were, you've got a quarter and 8 and so on, it's done all bounded and get a finite number. So the next condition says if we have, call it curly I, for a family of subsets, that's a set of subsets of the reals, is a set of disjoints of pairwise disjoint. Any two distinct elements of the set have non-empty intersection of pairwise disjoint subsets of reals. And henceforth, we're going to this disjointness condition is going to be quite common in this lecture. So henceforth, I won't bother to say pairwise. I'll just talk about a set of disjoint, meaning any pair of distinct elements has non-empty intersection. So if we have a set of is a countable set, then the measure of length we're assigning to the union, which is a disjoint union, they're also for the big union operation, unioning all the elements in the family. I'll write the plus inside to emphasize this disjoint. This is simply the sum over all the sum over the countably many subsets in I of lambda of x. So the sum of all. Okay. So the sum, the length of a disjoint union is the sum of the lengths of its components. And third condition. So this is called, this condition here is called countable additivity. And it plays a very major role in measurement. And the third condition is that the length should be translation invariant. It doesn't, you know, the length of this, it didn't matter where on the real line I drew this, it would have the same length. So for any subset of reals and the value d, which we think of as a displacement, which we're going to translate the set by, the length of set x displaced by d is the same as the length of set x. So here, x plus d, by definition, of course, means set of all y plus d. Well, let's put little x, set of all little x plus d for x being x. Okay. So these seem like reasonable conditions to have for a length function, and there's no way of satisfying them all. That's what Vitali's theorem says. Right, so in order to give the proof of this, I just want to observe that some other natural properties we might assume of length functions follow from this. So, we observe the following consequences. the bullet point assumptions. Just write a bullet point there. Just one bullet point assumptions. So, firstly, the length of the empty set is 0. Can't quite remember. You can view it as a special case of this, but it might, because the countable means finite or countable, and finite can be empty. So let's, for the moment, view it as a special case of this, but there might be another way of getting it to do.
From the first bullet point.
But we don't have a
condition,
we don't have a monotonicity condition yet.
No. The condition is that A has to be strictly larger than B, so we can get the empty set.
So we can't. Yeah. Although we could put this in that. Anyway, this follows. Right, so I'm getting it from this that curly I is the empty set, but there might be another argument for it too. For any x in the reals, the length of the singleton function is also 0. And for this, you can, for example, let's get that the length of the singleton 0 is 0. Well, the singleton 0, let's consider the open interval from -1 to 1. That's a disjoint union of the open interval from -1 to 0, the singleton 0, and the open interval from 0 to 1. And the length of the open interval from -1 to 1 is 2. The length of the other two bits of that disjoint union are 1 and 1 each. And so there's only 0 amount by the countable additivity. There's only a 0 amount there. Yeah. Okay. Once we've got that, then the length of the closed interval. Let's again the round bracket stuff. This is again B minus A because we're simply disjoint unioning two singletons at the end onto the open interval. Around the turn of the 20th century, around 1900, it was very early in the development of measure theory, we came up with this construction. But it's not very difficult, but it's a beautiful idea. So I rubbed out the theorem that we're going to prove, but never mind. And prove. We're going to define an equivalence relation on the reals. So I use a typical equivalence relation notation for on R by X is equivalent to R equal to Y if and only if they differ by a rational number. So if and only if Y minus X is rational. And we're now going to also look at, so we also consider the restriction of this equivalence relation to the interval 0, 1. Okay, so it's obviously an equivalence relation. Then we have the restricted equivalence relation also of 0, 1. And now remember that one of our equivalents of the axiom of choice was that every equivalence relation has a set of representatives. Okay, so by AC, let K be a set of representatives. So these are representatives for equivalence classes or for the equivalence relation on 0, 1. So K is a subset of 0, 1. So remember, a set of representatives is a set that intersects with every equivalence class in a singleton. So a set that contains exactly one member of every equivalence class. Okay? So here, let's flag it in red. Here we're using the axiom of choice. And what we're going to show is there's no consistent way of assigning a length to K. All right? So if we're going to assign it a length, that length will either be 0 or it will be non-zero. And if it's non-zero, well, it needs to be a value between it can at most be 1 by this monotonicity property. I mean, the closed interval has by the way, am I using the closed interval here? In the notes, I use the open interval. It probably doesn't make any difference, but let's just be safe. You know, nothing changes from what I've said. But let's just be safe and use the open interval. Okay. Anyway, by the assumptions we've had that the length of the interval is 1 and the monotonicity property is clear, it's clear that the length of K will be a number between 0 and 1.
Yeah, also these brackets.
Yeah, thank you. Also, so we're going to start off assuming the length is 0 and get a contradiction, and then we'll assume the length is positive, and then we'll also get. So suppose the length of K is 0. Well, then we have the length of the real numbers is the length over disjoint union, the countable one because it's indexed by rational numbers, of the sets K plus Q. Why is this? Firstly, every real number differs from a number in the interval 0. For every real number, there is some number in the interval 0, 1 that differs from that real number by a rational. Okay. You know, take pi. Well, then I can take pi minus 3, and I get a number in the interval 0, 1 that differs from pi by a rational number. And every real number differs from actually infinitely many numbers in the interval by a rational number. And therefore, and then you can take the representative of that equivalence class, you take that number that differs from the real number by a rational, you take the representative of its equivalence class, and that, of course, also differs from the original number by a rational. So for every real number, there's an element in the class in the set K that differs from it by a rational. But in fact, there's a unique such element K, because if there were two, they would differ from each other by a rational, and they can't both be representatives for the same equivalence class. So that basically is an argument that this disjoint union holds. Every real number is in exactly one of these sets. There's exactly one Q. Sorry, there's exactly one. Yeah. For every real number, there's exactly one element K for which that real number differs, from which that real number differs by a rational number. And there's only, and obviously the difference is exactly one rational number. It's just a, it's just the difference. So it's in exactly one of these steps. And then by countable additivity, this is the sum over the rational numbers of the length of K plus Q. So this is countable additivity. And then by translation invariance, well, here we're translating K by Q, but that's the length of that translated thing is the same as the length of K. So this is the sum. One summand for every rational number of the length of K. And this is the sum of zero countably many times by OSH. So this is the sum of indexed by rational numbers of zero, and that's zero, which is not equal to infinity. And the length of the real is totally infinity. There we get to contradiction. Okay, so it did not work for the size of K to be zero. So we're forced to get, so we have shown that the size of K is greater than zero. But then if we again consider now the length of, we're going to again consider a disjoint union where here we're going to only consider rational numbers in this case, the closed interval 0, 1. We're going to consider the length of this set, or because it's the length of a disjoint union. Sorry?
Shouldn't be intersection.
This.
So Q intersection.
Oh yeah, it should be. Yes, thank you. Yeah. Because we want this to be a countable disjoint union. So this is over those rationals of the length of K plus Q, which is now sum over those rationals, of which there are infinitely many, because of course there are infinitely many rationals in the interval of. So again, we've used countable additivity, translation invariance, and now it's a sum of infinitely many copies of a constant number, which is of course infinity. But yeah, we're obviously having network issues today. Anyway, it doesn't matter. So sorry, what's the
So we are working with the open interval, but here you're using square, so you're.
So here I'm using the closed interval.
Okay.
It actually doesn't matter.
Okay.
We could have perfectly, I'm just being consistent with my notes, but we could have perfectly well used the open interval there. The same thing is going to hold. But if we look at this, K is a subset of the open interval 0, 1. And we're translating it by a rational number that is at most 1. So this set, this set is a subset, let's write it like that. It's a subset of 0, 2. Okay, so the length of this is less than equal to 2. Because here we've got a subset of this interval. And once again, we've got a contradiction because infinity is not less than 2, so contradiction. And essentially what the problem is the way we've defined this K, the real numbers are this countable union of disjoint, of essentially translations of K. But the K is so the K is so sort of diffuse. It's like it's a bit like what do they call it? An aerosol, like sort of just like dots here and there in a kind of very diffuse way. The K is so diffuse that you have essentially between the interval 0, 1 and 0, 2, you can fit countably many copies of K. So either disjoint copies of K. So either if it has weight 0, then you don't get any mass for the whole of the interval, and that would be wrong. And if it has positive weight, well then, because you can squeeze infinitely many disjoint copies into this space, it can't also have positive weight. So there's something like that going on. Anyway, it's 5 past now, so let's have the break, and we'll have a break until 20 past. Are there any questions? Quick questions. Right. Okay, so what we've seen is there's no well-behaved function lambda from the set of all subsets of the reals to commutative lengths. And the problem was the reason for this is difficulty we found was that we had problematic sets for which we can't define a length. So in the proof, this was K, and this is such sets are called Vitali sets. After Vitali, as I said, it was Vitali scale. It's an example of a Vitali. Now, in mathematics, it's very important to have a notion of length in one dimension, just as it's important to have a notion of area in 2 dimensions, and it's important to have a notion of volume in 3 dimensions. And there are lots of notions in physics related to this, like mass, for example. Well, anyway, there are connections with many physical concepts involved here. So we need to be able to deal nicely with length. So what, we don't have a nice theory of length on arbitrary subsets. So what can we do? And there are essentially 4 different routes we can take to resolving this. There are 4 ways of dealing mathematically with length and related concepts. So one is to weaken those assumptions we had on the length function. So one possibility is to drop the countable additivity, and that can be weakened to something called finite additivity. Which the obvious weakening, weaken countable additivity to finite additivity. And some philosophically minded people have argued that this is a philosophically justifiable thing to do because you don't really get countable unions in the real world. Although, well, anyway, let's not go into too much discussion of that. So mathematically what happens is there does exist a finitely additive length function. It's not a canonical one, but there do exist finitely additive length functions satisfying the other assumptions. And that works in 1 and 2 dimensions. That does not work in dimension 3. So this. So, and also, yeah, so anyway, this works. It works for the reals. And I think, although I haven't brushed up on this for a while, I think for the plane, but not for 3-dimensional space. And in fact, we're going to see why this fails for 3-dimensional space, and the reason this fails for 3-dimensional space is the Banach-Tarski theorem, which is going to be the remaining main thing we do in the lecture. But we'll put that on pause for now, and we'll consider the other approaches. So, okay, so that would be weakening countable additivity. Another possibility is to drop the translation invariance. I mean, that's a very natural property, but you could say, well, if you can't have it, well, let's try dropping it. So to drop translation invariance, and then it is consistent with the axioms of set theory that there exists a translation variant measure as long as certain large cardinal assumptions exist. And in fact, the existence of such a thing such a measure is essentially a large cardinal assumption. It's related to the existence of something called measurable cardinals. So one gets into hairy territory, like the hairy in the sense of stuff that might freak you out a little bit. You have to think in very, very large infinities in order to work with this. So, so this is related to measurable cardinals.
I have a question about this. So does here for DRC proof, is this set theory or these 2 set theories sufficient to prove that such a function exists?
No,
No, okay, so we need measurable cardinal assumptions to prove that it exists.
Yes,
Okay.
indeed. Yeah. And moreover, it's equivalent to a measurable cardinal. So you really do need a measurable cardinal suffices and is sufficient. Sorry, that sounds like the same thing. Well, anyway, it's equivalent. But the third option is to do what probability theorists do and measure theorists do, what is considered the standard approach in mathematics, and that's to weaken the requirement that we measure arbitrary subsets. I mean, our problem with some strange subset constructed using the axiom of choice. So let's just accept we can't measure all subsets. We can measure just good subsets. So this is the preferred option in mathematics. Strict lambda to let's one sometimes uses a curly E for it, like what's called the sigma algebra of events in probability, where this curly E is a proper subset of the power set of the reals. Okay, so just a collection. So the idea is here where E is this is the third option where E is a collection of well-behaved subsets, and such sets are called measurable. So we need a notion of measurable subset of the reals, and we can assign weights to measurable subset. And we tell this that, we still have the axiom of choice. We can construct a Vitali set, but the Vitali argument just shows us that the Vitali set is not measurable. Okay? The Vitali sets are not measurable. Of course, very enticing possibility, which is something I like very much, is to drop the axiom of choice. And then if you don't have the axiom of choice, then it is consistent to have such a. But you can keep dependent choice. And with dependent choice, it is consistent to have a well-behaved measure on all subsets. And the reason for that is, well, I mean, the Vitali set is not a problem anymore because the form of choice we use to get it is not dependent choice. We use the real axiom of choice. The real axiom of choice to get the Vitali set through. The Vitali sets don't get in our way, and in fact, there's a consistency proof by Robert Solovay from the early 1970s that this is possible. So this is so I write CF, which is an acronym in English for compared to. I'll just mention a buzzword, which is Solovay's model of vector. But I don't really want to go much into that. Well, anymore into that at all. But
I have a question.
Yeah.
Yeah.
And let me just put a green ring around this because this is, mathematical orthodoxy says this is the good thing to do, and the whole of measure theory and probability theory and so on has been developed on this basis.
I have a question. So does df plus dc prove that there exists a function? No, it doesn't. Okay.
No, it couldn't. Because then if you could prove there exists one, then you could also prove there exists one in the axiom of choice, and we could find an inconsistency. So it's simply consistent with that choice. That's the determinant choice. Okay, so this is the preferred option, but I want to have a look at not really, I mean, so as I say, the first option turns out to be problematic in dimension 3 because of the Banach-Tarski paradox. I want paradox or theorem. So I want to spend the rest of the lecture telling you about the Banach-Tarski theorem because, to my mind, it's one of the most interesting consequences of the axiom of choice to get one's head around because it's really thought-provoking. I'm not going to relate it so much to this property 1 here. I'm just going to look at it in its own right. So the existence of these non-measurable sets, they're kind of hard things to visualize, even on the real line. As I say, it's like a sort of aerosol kind of thing, hard to know where it is. The fact that we have a set that we can't measure its length is a bit strange. And the Banach-Tarski theorem shows us, I think, that it fully exhibits the extent of the strange. It really underlines how strange it is. So I'm just going to state the theorem straight away. Banach-Tarski theorem. And it's also known as a paradox because it's so counterintuitive. But it's not a paradox. It is just a theorem of set theory with choice. So just hands up, by the way, if you know what the Banach-Tarski theorem says. Okay, you've all met it before. Have you seen it formally stated? So we're going to at least formally state it, and then we're going to actually prove it as well. So, but in order to formally state it, I need a cheat sheet. So it's about the closed unit ball. So I'm going to use blackboard B for the unit ball. Be the closed unit ball. So the closed unit ball is, to remind you, it's a set of points in three-dimensional space. We're going to consider the one centered at the origin. So it's x, y, z. So we distinguish the ball from the sphere. The sphere is the points at distance 1 from the origin. The ball is all the points at distance, if it's closed, at distance less than equal to 1 from the origin. So square root of x squared plus y squared plus z squared is less than equal to 1. So then the theorem says that B can be partitioned into finitely many pieces. So we're going to divide the pieces into 2 groups, the A pieces. So we're going to have M A pieces and N B pieces. And just to emphasize, it's partition, so they're all disjoint. Such that there exist proper rigid transformations Does anyone know what a proper rigid transformation is? I'm going to call them theta and phi. So we've got n thetas for the A pieces and n phi's for the B pieces. Does anyone know what a proper rigid transformation is? Or what a rigid transformation is?
Oh, maybe for the rigid transformation, is this a transformation that preserves distances?
Right, okay, yeah. A rigid transformation is a transformation that preserves distances, exactly. And the rigid transformation can then be decomposed as a combination of translations, rotations, and reflections. And a proper rigid transformation is one that can be decomposed as just translations and rotations. Because in the real world, you can do translations and rotations, but you can't do a reflection on a rigid body. You can view your reflection, you can't perform one on something. So these are ones that you can actually carry out on your pieces of your sphere. Such that, oh, well, we've already got such that, so we've already got to such that, so we'll say for which. When we rigidly transform the A pieces, they remain disjoint. So moving them around, but keeping them separate from each other. And we get the whole of the unit sphere back from, so sorry, this is theta 1, A1. So we're moving each piece. There's an M here. We're moving each A piece by its transformation. They stay disjoint and we get the unit sphere back just from the A pieces. And moreover, moving the B pieces around, so under the phi's, they also stay disjoint. And we get the sphere back from the B pieces. Right. So okay, this gets back the unit sphere around the origin. But if we did some more, if we added like some translation to this, we could get this sphere at the origin and this sphere like 3 away or something like that. So they'd be disjoint. And essentially, we can move the A pieces and the B pieces to get back 2 complete unit spheres, just made out of pieces that came from 1 unit sphere. So it's very, very weird. Either way, for moving them around, so the disjointness is here. When we've moved the pieces, they're disjoint. But nothing I'm going to say today tells us that they don't overlap with each other on the way. But in fact, somebody has proved that the Banach-Tarski theorem can also be strengthened by saying the whole carrying out the rigid transformation, the pieces always remain disjoint from each other. So the point is, I mean, this is why it's so famous. You can cut up, you've got your solid ball of gold, you can cut it up into finite many pieces, reassemble them, and you get back 2 solid balls of gold. So it would be a very useful thing to be able to carry out in practice. And of course, yeah, the reason it's going to hold is because these pieces are going to be like Vitali sets. So they're going to be non-measurable pieces. They could not be assigned any math. And that's the key that's going to make things work. But nonetheless, to be able to get this, to engineer this situation is going to require quite a lot of ingenuity. And so our hero today, Banach, was involved with this together with Tarski, a very famous logician. Yeah. Right, so what I want to do in the remaining time, and we'll see how far we want to go into details. I want to present you some ideas in the proof so you get some flavour of how this very counterintuitive, this very counterintuitive result works. And there's a really lovely book about this called The Banach-Tarski Paradox by, put it in the notes, by Stan Wagen, or Wagen, I don't know. The Banach-Tarski, I just write BT paradox. By Stan Wagen. And I'm not going to have time for all details in the lecture, if you're interested in seeing more details and some nice discussion about the results, then I'd recommend that book. It's in the library. This department. And I'm going to follow the proof outline. But I'm going to give only an outline of the proof, and I'm going to follow his approach to the proof. So the proof involves group actions. So just to see, hands up if you know what an action of a group is. Oh, goodness me. So this might be a bit challenging. What's the slogan for action of a group? Does anyone know?
Maybe just axiom. Maybe we don't have like a special solution.
So the group you know what a group, hands up if you know what a group is. Okay, good. Right. So given a group, an action of G on a set X is a map. You normally write with a dot. You give it a left side and a right side, so it's written infix. There are two notions. There's a left action and a right action. We're going to stick the group on the left, so this is the left action. But the point is, you have a function that transforms the set given an element of the group. And there are axioms it needs to satisfy, but irrespective of the abstract concept, the version, the one that's going to be important to us is easy to understand. So we're going to be interested in. Sorry? You have? Okay, good. The one we're going to be particularly interested in is the action of the special Euclidean group of dimension 3, which is the group of rigid transformations. So every rigid transformation, it's a combination of translations and rotations. Such things form a group because you can always undo them, right? So they have inverters, and the identity of the group is just the translation that doesn't move anything, and that's the group of translations, and it's an action on three-dimensional space. When you perform such a thing, you move three-dimensional space. You either translate it or rotate it, or a combination of translation. So we view it as an action of three-dimensional space. Okay. Now this is not part of the three, but this is like all the things. This is represented by certain matrices together with translations, and then we get back. Okay, so that's the action we're interested in. But the point is that the main notion that we're going to need is really a property about group actions. So just for any group action, but we're going to think of it as a property of this. We're going to consider the notion of so I've divided the proof into a large number of steps, and this is the first one. And this is the notion of G equi-decomposability. So given such a group action, we say that subsets A and B of X, and we're thinking of this as thinking of X as three-dimensional space, so sets of elements and three-dimensional subsets of three-dimensional space are G equidecomposable, if they can be partitioned as, so we can carve up A into M parts and B into N parts, disjoint parts. In such a way that there exists, oh sorry, it's N parts here. There exist elements G1 to Gn group such that B1 is B1 can be obtained by moving A1 under the group, and Bn can be obtained by moving An under the group via G1 to Gn. But so what this says in terms of three-dimensional space is two subsets of three-dimensional space are equidecomposable if we can chop them into the same number of pieces in such a way that each of the pieces, each paired elements of pieces each piece can be transformed to its pair on the other side. Yep.
So this group G, since G1 to Gn are functions, it's the
G1 to Gn are elements of the group,
yes.
but we're applying them, here we're using the group action.
Okay.
We're applying the group action to, so the group will map any point of the set X, and so we can also map a whole subset of the set X. So this equity composable, we write it as the notation is A is related to B under the group G, and it's an equivalence relation. It's easy to see that it's reflexive and reflexive and symmetric. Transitivity requires a proof, but we won't go into the details of that. But the reason for introducing it is we have a restatement of the Banach-Tarski theorem. Aha, I'm rubbing it off so we can remember what it said because it's very easy to visualize. So this is the first restatement of the BT theorem, is that we can partition the ball as, so now we're going to cut it into two pieces, where we think of A as the union of the A1 to AM that we had before, and B as the union of the B1 to BN that we had before, where each piece is equidecomposable with B, such that the is equidecomposable under our group of rigid transformations with A, so the ball is equidecomposable with A, and the ball is equidecomposable with B. Okay, so it's saying the same thing as before. We have two separate bits of the ball, namely those that we're going to assemble to one copy of the ball, and those that we're going to assemble to the other copy of the ball. And what does assembling them to one copy of the ball mean? Well, we can then cut it up into a finite number of pieces and move them around to get the ball back. Okay, so that's, we can say we cut up A into a finite number of pieces and move them around to get the ball back. And it's the same, we cut B into a finite number of pieces to get the ball back.
I have a question here. So
Yeah.
the definition, in the definition, if A and B are equally composable, we have an initial decomposition of both of them. And I'm interested what the initial decomposition, so to speak, of the ball is here. Because they also have to have the same number of pieces, namely M.
Yeah, so here the decomposition of A is going to be A1 to AN.
Okay.
And the decomposition of the ball is going to be what we get from the ball cut into the pieces when we've reassembled these A1 to AN to get the ball. We were reassembling them as disjoint pieces, and that gives us the partition of the ball. Okay,
from just M pieces.
Yeah, well, we're moving these N pieces. So we've got N pieces here, and we move them, and we never duplicate a piece.
Okay.
So in the Banach-Tarski theorem, you're cutting the ball up into a finite number of pieces, and once you've got the finite number of pieces, you keep those pieces the same.
Okay.
So here we're dealing with the M pieces, A1 to AN, in the statement of the theorem before, and we get back the same N pieces in different places reassembled as a ball. And here we've got the N pieces here, and we get back the same N pieces reassembled as a ball.
Okay.
Okay. Good. So we have the first restatement of the Banach-Tarski theorem. And we're going to use this to get to a second restatement, and then the second restatement will be what we can prove. And to get the second restatement, we're going to look at a little bit more at this G equidecomposability, because there's actually an associated pre-order. So a pre-order is just a symmetric, not symmetric, a reflexive transitive relation. It's like a partial order, but it doesn't need to satisfy the anti-symmetry part. And so whereas this is saying A and B can be, you can get B from A or A from B, doesn't matter the direction, by cutting one of them up into a finite number of pieces and moving them around to get the other. That's essentially what this says. The pre-order is going to say, it's going to have a direction that is going to say we can get some subset of the thing on the right by cutting the thing on the left into finitely many pieces. Whereas the pre-order so this holds if there exists subset of B that is equidecomposable with A. Okay, so we can just cut A up into a finite number of pieces, move them around, and get a subset of B as a result, keeping them disjoint. Such that A is equidecomposable with C. And there's a beautiful result about this, which is that if we can decompose A and move it around to get a subset of B, and we can decompose a B and move it around to get a subset of A, then they're equidecomposable. So it turns out we can actually, under those conditions, cut A up into a finite number of pieces, move them around, and get exactly B back. And then they're equidecomposable. And this is one of these situations in which we have a relation that's obviously reflexive and transitive. And it enjoys some sort of anti-symmetry property, not with equality, but with equidecomposability. And that is a relatively deep property. Does the situation remind you of anything? We've got a relation that's easily.
The Schroeder-Bernstein.
Very good. So it's very like the Schroeder-Bernstein theorem. And in fact, this is the Banach-Schroeder-Bernstein theorem. The Banach. So Paul Cantor had his name removed, but anyway, it should have been Dedekind, as we discovered. But anyway, it's the Banach, Schroeder and Bernstein, keep their names so that people know what we're talking about. It is, this was Banach that proved this theorem, but it's right to put some reminder of the Schroeder-Bernstein theorem in, because the proof is basically the proof of the Schroeder-Bernstein theorem. So you prove like the proof of the Cantor-Schroeder-Bernstein theorem. And that's a nice exercise to prove that. Right. So, yeah. So it's 4 o'clock. I think that's a good stopping point. I'm going to use this 15 minutes to think about what it's going to be appropriate to say in the last hour of the lecture, because obviously things could potentially get a bit technical, and I think what's important here is to give you just like a try and do a high level flavour of it. So right, any questions before we break? Okay, right. So we start again at 15:15. So we've got one short, hopefully, hour left. Not enough time to cover the whole theorem, and I also think it would be maybe a bit too technical anyway to go all the way. So looking at the material, it actually looks like the best thing to do is simply go about halfway, because about halfway we get where the axiom of choice is used. And at that point, we also get the first the first kind of geometric decomposition result that applies in a geometric situation. You'll see what that geometric situation is. Then there are a number of tricks to take to go from that situation, which will involve the subset of the sphere, to the whole ball. And for those, you can look at the notes. I don't want to dwell too much on the details of anything, because I want to keep things reasonably high level. The next thing to do, we've got this restatement of the Banach-Tarski theorem using this notion of equidecomposability, and we now also have this pre-order associated with equidecomposability. And what I want to do first is well, what we're going to get to is another restatement of the Banach-Tarski theorem in slightly more manageable terms. And I'm going to, in order for anyone who wants to look at how it's done in the book, I'm going to follow the approach there. So it involves now introducing a notion that's a bit more general than it really needs to be just to prove the Banach-Tarski theorem. So we're going to introduce another notion that's going to allow us to restate the theorem. And this is the notion of what's called a paradoxical set. So we've got a set X that has a group action on it. And ultimately, we're thinking of the set X as being three-dimensional space and the group as being the group of rigid transformations. But for the moment, it's still just an abstract group action, the value grouper. And we're going to say that a subset of our space X is paradoxical with respect to the group G paradoxical. Essentially, if the whole set itself can be recovered from two disjoint subsets of it. Okay, so but the recovering means we're allowed to split those subsets into finitely many pieces and move them around. So if there exists disjoint A1 to AN and B1 to BN, so like in our original statement, we don't have a different N and N, so like in our original statement of the Banach-Tarski theorem, so these are subsets of B. And group elements, so the G1 to GM are like our thetas, and the H1 to HN are like our phi's from the original theorem. The group elements such that the A pieces assemble E. So we carve the disjoint pieces out of E, that the A pieces on their own suffice to recover the whole of B, and the B pieces as well, if we move them around. Also suffice to recover the whole of B. But what we don't ask for, which is different from the, that's not a good one. What we don't ask for, which is, and this is different from the original statement of the Banach-Tarski theorem, is we don't require these unions here to be disjoint. So we might have overlapping pieces to recover these. And we also don't require the A's, the disjoint union of these are disjoint, but we don't require the disjoint union of these pieces to be the whole of it, which we had originally with the Banach-Tarski. So we've weakened what we're doing to E. We're only taking a subset of E and partitioning it in finitely many pieces, and we're recovering E, allowing some overlaps in how we get there. Okay, but it turns out that these restrictions, this weakening is actually an inessential weakening, because an E is G paradoxical in this sense, if and only if we can actually partition the whole of B finitely many pieces and recover E using disjoint, by using disjoints. And we can state that easily because using the notation we've got, so that's a proposition, which is that E is paradoxical if and only if there exists, if and only if we can partition E into two pieces such that both A and B are equidecomposable with it. And essentially what that's saying is we would have got the same notion if we'd made this an equality here, and if we'd required that we get disjoint unions here at the end. That's essentially what it's saying.
G paradoxical. E is G paradoxical.
E is G paradox.
E, okay.
Yeah. Very good. And to prove this, well, it's obvious that the right to left trivially implies the right to left holds trivially because this is the stronger property. The left to right, well, actually it's easy to get the disjointness property here because you simply start off with your original A1 through to Bn, for which these things might not be disjoint. But whenever you then move through them one by one, whenever you get a bit of overlap with something you've already looked at, you just remove that overlap and then you transport it back along the inverse group operation and you remove it from the original set. And you still would get disjoint sets, but you're even more of a subset of E then. So getting the equality with E, that's the tricky bit. And there's a really neat argument for that using the Banach-Schroeder-Bernstein theorem. So that comes to the rescue. But once we've got this, we can now state the second reformulation of the second restatement of the Banach-Tarski paradox, which maybe I'll put it here below the first one. Of the BT theorem. And we can put this on one line. It's simply that the unit ball is SE3, so it's paradoxical with respect to the group of rigid transformations of three steps. Because this proposition tells us that that holds exactly when this is the first restatement of Banach-Tarski theorem. Okay, so this is what we're going to prove. We're going to prove that the unit ball is SE3 paradoxical, and that means we don't need to worry about disjointness here. Actually, that's not really an issue because everything we do, the disjointness will just be there, just naturally. So actually, that doesn't really help us. But what does help us is this subset property. We don't need to take pieces, we don't need to partition the whole of the shape we're working with. We can just take pieces from the subset of the shape. That's quite useful. And we're going to immediately use that. Well, actually, maybe I'll go over here. Oh no, maybe I'll put it here. So what we're going to do is we're going to work towards the unit ball being paradoxical by showing various things that are paradoxical. And the useful tool we're going to have is the following lemma, which is easy to prove. Not all the properties have been easy to prove. For example, the Banach-Schroeder-Bernstein was not so easy to prove, but this is easy. So if you've got some G paradoxical set E, and it's equidecomposable with an E prime, so we can cut E into finitely many pieces and move them around to get E prime, staying disjoint in this case, then E prime is also G paradox. Right. Okay, so we want to establish from paradoxicality. And the first result we're going to do is about a very simple group. And then we're going to build on this to get to the geometric situation. And this simple group is, I don't know how much algebra you've all done. Have you done constructions of free groups? Hands up if you've done a free group. The next step is the paradoxicality, the property of being paradoxical. Of F2, which is the free group on two generators. So hands up if you know, if by hearing free group on two generators, you know what that means.
I meant what the free group is in the category theory class.
Oh, I see. Fortunately, the free group on two generators is easy to introduce. So the free group on two generators we can view as its elements are words or finite sequences, if you like. I use words because I'm a computer scientist at heart. Words over the alphabet, where we give ourselves four symbols, A and B, those are the two generators, and we give ourselves another symbol, A to the -1, which is going to be the inverse of A, and B to the -1, which is the inverse of B. And the idea, we've got two words and we can multiply them by concatenating the words. So an element of the groups will look like A, B, B, A to the -1, B, A to the -1, B to the -1, B to the -1, A, something like that. So this is, we're multiplying little a by B, by B, by A, by B, by A to the -1. But when you multiply an A and A to the -1, the point of A to the -1 is the inverse of A, so it should cancel. So actually, we can form this multiplication in the group because we're simply multiplying some elements of the group together. But we want a nice representation of it. And when we get an A to the -1 together, they cancel. So we remove that. And then we're going to get a B and a B to the -1 together. So they cancel. And also they would cancel the other way around. So this is A, B, B, A to the -1. This B cancels with that B to the -1, B to the -1, A. Okay, so it's words over the alphabet A, B, A to the -1, B to the -1 that do not contain consecutive, that means next to each other, A and A to the -1 in either order, or consecutive B to the -1. And such words we call such words reduced words, i.e. reduced words. And multiplication of W, that's one reduced word, times another reduced word, W prime, is defined to be concatenate W prime and then reduce. Because in concatenation, you might be multiplying BA by A to the -1, B to the well, then we get the identity, but then it doesn't matter. Let's say BA by A to the -1B, concatenate them, BA, A to the -1B, and then you reduce, you take out adjacent pairs of a generator of its inverse, and you get back dB in this case. So concatenate and reduce. And this is a group. Its identity is the empty string, the empty word. If I use a backslash of R epsilon for the empty word, the inverse of a word is just inverse all the symbols in the word and also reverse the order of the word, and that will give you the inverse. It's a non-commutative group, so not an abelian group. So little ab is not equal to b a. The identity, you just have the identity of words, but it is the free group on 2 density. And this group, like any group, acts on itself by multiplication. And we're going, so that's called the transitive action of a group on itself. And we're going to consider that as a left action. So the group part, the acting group is on the left, and just like we've been doing all the way through, and the part being acted on is on the right. And we want to show that this is paradoxical. So I'm going to keep the restatement of the Banach-Tarski theorem. So we're going to do this at the bottom of the board. So F2 is paradoxical. Is F2 paradoxical? So to see this, we notice that F2 can be written as the empty word as a disjoint union of the empty word what notation do I use in the together with, well, the disjoint union of all the words starting with the symbol little a, all the words starting with the symbol little a to -1, all the words starting with the symbol little b, and all the words starting with the symbol b to the minus. That's just obvious. But then we see that so also F2 can be got as words beginning with A, and in fact it's a disjoint union with the action of A, of the little a itself, on words beginning with A to the -1. Because this set of words, every word will start with A to the -1. That will cancel with the A. And then you'll have just the remainder of this word, everything apart from the starting letter. The remainder of that word can't begin with an A because we're looking at reduced words here. So we don't have an A to the -1 and an A next to each other. The remainder of this word, it could either be empty, in which case forget this, or it could start with any symbol other than A. So we get, the union of all other options from that. And this is also, an F2 is also the disjoint union of WB together with B acting on WB to -1. So what we've done here is we've partitioned a subset of F2, namely everything apart from the empty word. This gives us an A1, this gives us an A2, this gives us a B1, this gives us a B2, in such a way that we can move them around, the two A pieces around, and get back the whole of F2. And as I said, the fact that we would be allowed an overlap here is not really important to us because we've managed to get a disjoint union anyway. And again, the same thing here. But what we have really used is that we're only taking pieces out from the subset of F2. We've left the empty word behind. We are using that possibility. But in fact, in this case, we always know that it's the same as that equipartition property, that stronger property that was in the proposition. And in this case, the proof does not get, to show the stronger property that we can partition F2 itself into A parts and B parts is not actually that much harder. You just need a few more pieces. But anyway, this argument shows the paradoxicality of F2. Okay, so very good. But what does this have to do with geometry? So now we get the crucial link with geometry.
Excuse me, does this, am I misremembering that for paradoxicality, we have to, for paradoxicality, we have.
So this is our A1 and our A2. We're using M is 2, N is 2. G1 is the identity element. G2 is little a. H1 is the identity element. H2 is little b.
Yeah. Okay.
And we're improving on what we need to do because we also managed to get this joint union. So the geometry comes in now, and this is, in a sense, the hardest thing to show. There is, in fact, I don't prove this, but I believe the details are in the book. This is not in the notes. There is a group embedding of F2. So the hook means an embedding. So embedding just means an injective homomorphism into SO3. Hands up if you know what SO3 is. So we're now happy in this lecture with SE3, which is the group of rigid transformations consisting of rotations about the origin and translations. SO3 is the group of just rotations about the origin, the rotation group. So it's a subgroup of SE3. And you can embed the free group onto generators in it. So hopefully you know that rotations are a non-commutative group. And basically, to embed them, you just take a random, we need to map little a and little b in such a way that we get back, that determines a homomorphism because it's a free group. But we need to make sure that that stays an embedding, so you map A, you just choose some irrational rotation about some axis. So irrational here means that there is no integer number of repetitions of this rotation, which will take you to a multiple of a 2 pi rotation of an all the way around rotation. Okay, so you're never going to get back to the same point again, however many times you rotate it. It takes some irrational rotation. You then take a different axis of rotation that is again at an irrational angle with respect to the first axis and might need to satisfy a bit more than that. And one way to make sure it works is to choose it randomly, and then with probability 1 it will work. And another randomly chosen irrational rotation about that axis. And then you've chosen everything sufficiently randomly or independently that it will be impossible to have two different combinations of those rotations amounting to the same resulting rotation. But to really prove that it can be done, I think the way the book does it is it just gives an explicit definition and then proves using by rolling up their sleeves and doing putting the effort in, proves that it really is an embedding. It always seemed to me that it might be possible to do an argument based on cardinality here, or there might also be possible to do a probabilistic argument that some sufficiently randomly chosen rotations are guaranteed to work. I've never seen the proofs done in that way, but I've never thought it through either, so I don't know. It would be nice to have a nice proof of this, but anyway, it can be proven, and it's that's in the book. And what we're going to prove from this is that we're going to prove something geometric is paradoxical. Okay, so there are various steps, and one of the steps is to prove that the two-dimensional sphere, so that's the surface of the three-dimensional ball, is paradoxical. And we get there in the notes, but I don't want to go even that far. What I'm going to show is that the two-dimensional sphere with a certain set removed is paradoxical. So this is SO3 paradox. Well, actually, we're going to prove this, and then another argument gets us that the surface of the sphere is paradoxical, and then once that's done that, you can get to the ball. So here, to prove this, we actually prove it as G paradoxical. Now we consider F2 paradoxical. So this should say F2. You know, so there's a correction to make. Now we're considering now F2 as a subgroup of rotations. So just special rotations. And if it's F2 paradoxical, it's obviously SO3 paradoxical because it's a subgroup, and the definition of paradoxicality is clearly if it's paradoxical for a subgroup, it's paradoxical for the whole group. So we're going to prove that this is F2 paradoxical, where D is the set of points X, Y, Z on the sphere, such that for every group element in F2, let's call them W because they were the non-reduced words, but we're viewing them as rotations now. Actually, I'll put G back, but it's a rotation because we're embedding the free group in the rotations. We're going to consider those points that are fixed points for the rotation. The set of all points that are fixed points for some rotation in F2. So G acting on X, Y, Z gives us back X, Y, and Z. Sorry? Yeah. Oh, sorry, yeah. Indeed, for some G, fixed point for some, and obviously G is not the identity because then every point would be a fixed point here. Then we would have nothing back. So the point is, if G is not the identity element, then it's a proper rotation. And there's the Euler rotation theorem from geometry that says any rotation of the sphere, any non-trivial rotation of the sphere has how many fixed points? Exactly two. Every combination of rotations is a single rotation. It has one axis of rotation, which gives us two fixed points, one at the two intersects of the axis with the sphere. F2 is a countable set because it's a set of words over a 4-element alphabet. So we only have countably many fixed points. So we're removing only countably many points from the sphere. The D is countable. Okay. Now, because this is the set of fixed points, F2 acts not just on the rotations, obviously act on the sphere, but we've removed these countably many points. It acts on this set with the points removed. So it acts on S2 with D removed. Because none of the rotations in the group F2 can take a point outside of D into D, because if it did, what's the contradiction? Well, it can't. I don't actually see the contradiction now. So we can visit that. We can revisit that at the end. I don't want to waste time on me trying to think that one through on the fly. So anyway, this is because D consists of the fixed points. I remember that. Consists of fixed points. Okay. So now, the group action acts on the sphere. We've removed countably many points. So then we need the notion of the orbit, the group action. So if you've got, I don't know what this is called in Slovene, but you've got a group acting on a set. You consider a point in the set. You consider all the elements to which the group can transport that point. That's called the orbit of the point. Okay? So the orbits partition the group, the set that's being acted on. So every point will lie in exactly one orbit set. By the axiom of choice, we can choose an element of each orbit set. So define K, I call it K, yeah, to be a set of representatives for orbits of F2 on the two-dimensional sphere with these countably many fixed points taken away. And now we can show that we can now show that the two-dimensional sphere with D removed is paradoxical, because the two-dimensional sphere with D removed is equal to the disjoint union of K itself together with the action, the set of all points we get by applying a word in this A1 to a point in K. So we simply stick K everywhere here, meaning this is the elements of K, there's the set of orbits. These are the representatives of the orbits. These are all the places we can get by taking a representative of the orbit and applying a transformation starting with A. All the places we can get applying a rotation starting with A to the -1, and so on, from the representative. And this is similar to the argument for the Vitali theorem. One shows that And we showed that the real numbers was the countable union of the countable union of translations of K by rationals in the case of the Vitali argument. It's a similar argument here provide this disjoint union holds. And now we have a new A1 and A2 and the B1 and B2. And we simply stick K here and here and here and here. Oops, K. And we get back the sphere with the set D removed. And that shows that the sphere with these countably many points is paradoxical. We then apply a trick to deal with countably many points. Having done that, we get that the sphere itself is paradoxical under rotation, so we can divide the sphere into two pieces. We can partition subsets of it into two pieces, into two subsets, each of which decomposes into finitely many pieces that we can rotate around to get the whole sphere back. Once we've done that, it's easy to get the decomposition of the ball apart from the center of the ball, because you just, for every point on the sphere, we can decompose the sphere into finitely many pieces and assemble one block to get the sphere back and the other block to get the sphere back. So now we can extend that to the sphere apart from the origin, the center of the sphere, just by moving rays into the center from the ball apart from the origin, by projecting rays into the center and just missing out the center and just moving them in the same way that the sphere is moved. And so then it just remains to deal with the center, and there's another trick similar to the trick we need to use here to go from here. We removed countably infinitely many elements from the sphere. From the ball, we've just removed the center. We need another trick similar to that when we get back to the ball itself. But that is, I think, as much of a flavor as I can give you of the theorem. The proof of the Banach-Tarski theorem, it can't be made examinable because it's obviously, I can't cover it in sufficient detail, and you've probably seen more details than you wanted to. Anyway, you want to see more details, but first at the lecture notes, secondly at the book, which has many more details. It's a beautiful book. I recommend it. So the proof of the theorem is not examinable, but the statement of the theorem and the knowledge that this theorem follows from the axiom of choice is examinable for the oral exam discourse. Okay, are there any questions? Right, well, so I think that's enough for today. Thank you and good luck next week at the exercise class in the quiz.